Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 37, and this is lecture number 15 of the Physical Chemistry chapter Liquid State. This lecture number 15 is the last lecture of this chapter Liquid State, and the subtopic of this lecture is effect of concentration of solutes on surface tension. Let's begin with two types of solution. Both are aqueous, one containing an electrolyte, for example salt, another containing a detergent. So if we plot surface tension as a function of concentration, then in one case we shall find that in this case for electrolytic solution, surface tension increases with increasing concentration, whereas surface tension decreases with increasing concentration in case of an aqueous solution containing detergent. So we have two cases. Case 1, surface tension increases, and case 2, this one, surface tension decreases. So in case of increase in surface tension with respect to concentration, that is the rate of change in surface tension gamma with respect to concentration C, this has a positive slope, that is this change is positive. And in case of surface tension decrease, the value d gamma dc is negative because gamma is inversely proportional with respect to concentration here. Now this case where d gamma dc is positive is known as negative adsorption, and this case where d gamma dc is negative, this is known as positive adsorption. You can see that the accumulation of the solid molecules in the surface in case of electrolytic solution is less than that in the bulk, whereas the accumulation of solid particles in the surface in case of detergent solutions is greater than that in the bulk. So here adsorption is positive and here adsorption is negative. This is the case 1 and this is case 2. So let's determine the difference in concentration of the solid particles in between surface and bulk, that is concentration of this one minus concentration of this one, and you can find it by means of the Gibbs adsorption equation. So at the starting, let us take a solution where N2 moles of solute is dissolved in a solvent containing N1 moles of solvent molecules, and the solution after mixing up has the surface tension gamma, whereas it has a surface area S. At a certain temperature and pressure, the Gibbs free energy of the system. What should be the Gibbs free energy? Here are three parameters. One is N1 number of moles of solvent. So if solvent has chemical potential mu1, then N1 mu1 is the free energy contribution from the solvent. If mu2 is the chemical potential of the solutes, then N2 mu2 is the contribution from the solid molecules. And finally, the contribution in free energy from the surface is surface energy, that is surface tension into surface area, that is gamma S. So the overall free energy at constant pressure and temperature is N1 mu1 plus N2 mu2 plus gamma S. This is equation number 23. And we know that mu1 and mu2 are the chemical potentials of the solvent and the solute respectively. So we carry forward this equation number 23 in the next slide, and if a little amount of solvent dN1 is introduced to the system, or if dN2 amount of solute is added or introduced to the system, as well as the surface area was also increased by small amount ds. So the amount of solvent has increased by a very infinitesimal amount dN1. The amount of solute has increased by a very small or infinitesimal amount dN2, and the surface area also has increased by a very small amount ds. So in that case, what should be the change in free energy? The change in free energy should be dG at constant pressure and temperature. Now what has changed? N1 has changed by dN1, so it should become mu1 dN1. Here in place of N2 we should write dN2, and here in place of S we should write ds. So the change can be detected as this one, dG at constant pressure and temperature equals to mu1 into number of increase in moles of solvent, so dN1, plus mu2, that is chemical potential of the solute, into the amount of the solute molecules which has been added to the solution, and plus surface tension into increase in surface area, so gamma ds. Now if you differentiate this equation number 23 in both sides, then you shall get another equation. What is the equation? Now this one is the equation. In the left hand side it should produce dg at constant pressure and temperature. Now it will have two parameters, n1 d mu1 and mu1 dn1. So n1 d mu1, mu1 dn1. Now differentiating this one, it gives n2 d mu2 plus mu2 dn2. So n2 d mu2 plus mu2 dn2. Now this one will also give two parameters. One is gamma ds plus another one is sd gamma. So gamma ds plus sd gamma. So this will produce equation number 25. Now the difference between these two equations will produce yet another equation. So subtracting equation number 24 from equation number 25, we have what we have here. Dg would be cancelled out by this dg. This mu d1 dn1 would be cancelled out by this one. This one would be cancelled out by this one, and gamma ds would be cancelled out by gamma ds. So what are left here? Only n1 d mu1, here n2 d mu2, and here sd gamma. So summation of these three terms is 0. So n1 d mu1 plus n2 d mu2 plus sd gamma is 0, and thus we get equation number 26. Now the system is supposed to be divided into two imaginary phases, such as the surface phase and the bulk phase, like this. This is the surface phase and this is the bulk phase. So you have the solvent molecules n1 number and solid molecules n2 numbers. So n1 is nothing but n10 plus n1 prime. N10 is the number of solvent molecules present in the bulk. N1 prime is the number of solvent molecules present in the surface. Similarly, N20 is the number of solute molecules present in the bulk, whereas N2 prime is the number of solute molecules present in the surface. So what is the overall number of molecules in the surface? Now N1 prime plus N2 prime. So this is the surface phase. Whereas in the bulk phase, there are N10 plus N20 number of molecules in the bulk phase. So number of moles in the number of molecules will be represented by the unit mole. So number of moles in the surface phase, solvent has N1 prime and solute has N2 prime. In the bulk phase, N10 number of moles of solvent, N20 number of moles of solute. So that N1 equal to N1 prime plus N10, that is number of solvent moles in the surface plus number of solvent moles in the bulk. I am saying two things. One time I am calling it molecule, another time I am calling it mole. So what is the difference between two? Mole is the unit of number of molecules. So both are correct. Okay. N2 is the number of moles of solutes. Contribution from the surface is N2 prime and contribution of number of solutes from the bulk is N20. Now we carry forward equation number 26 in the next slide. What is the equation number 26? The N1 d mu1 plus N2 d mu2 plus sd gamma equals to 0. Now we have to apply these equations in the surface phase as well as in the bulk phase. So in the surface phase we have N1 prime and N2 prime, and in the bulk phase we have N10, N20. So we shall get two equations. One is N1 prime d mu1 plus N2 prime d mu2 plus sd gamma, and in case of bulk phase there is no surface, so this term would vanish. Only N10 d mu1 and N20 d mu2. So this is the equation for the surface phase, which is derived from equation number 26. Thus we get equation number 27, and equation number 28 would be obtained from equation number 26 similarly, but this sd gamma part would not be present here because the bulk does not have any surface. So equation number 27 and 28. So this is the ratio of number of moles of the solvent in the surface is to number of moles of solvent in the bulk. So we have to multiply the terms of equation number 28 by this ratio or fraction n1 prime by n1 0. If we do this, then this one when multiplied by n1 prime by n1 0, then n1 0 would be cancelled out, only n1 prime would be left here. So this would become n1 prime d mu 1. And if you multiply this term with n1 prime by n1 0, nothing is cancelled, so it becomes n1 prime into 0 by n1 0. So multiplying both sides of equation 28 by n1 prime by n1 0 with this fraction, if we multiply, then equation number 29 is obtained, and equation number 29 is n1 prime d mu 1 plus n2 0 n1 prime over n1 0 into d mu 2 equals to 0. So we have to subtract this equation from equation number 27. Okay, what is equation number 27? Let us remind it. Equation number 27 was n1 prime d mu 1 plus n2 prime d mu 2 plus sd gamma equals to 0. It was equation number 27. So if you subtract this equation number 29 from this equation number 27, then this term would be cancelled by this term, but this one would be left uncancelled, this one would be left uncancelled, and this one would become negative because you are subtracting equation number 29. So this way we shall get yet another equation, and this equation is n2 prime d mu 2 plus sd gamma minus n2 0 n1 prime by n1 0 d mu 2. Okay, so look at this. This is the equation: n2 prime d mu 2 plus sd gamma minus n2 0 n1 prime over n1 0 into d mu 2, and this is equal to 0. And if you take d mu 2 as common, then it would become n2 prime minus n2 0 n1 prime over n1 0. So this term is kept within the bracket, and separate term here is sd gamma is the second term here. And if you rearrange this equation like this, you will get this form, and finally you will get the expression of d gamma over d mu 2. Then this minus s would go to the denominator of this equation, and if you just interchange this minus sign from left to right side, then it becomes minus d gamma by d mu 2. So this way you get equation number 30, which has the form this one. Now, do you know what is the physical significance of this term within the bracket, or overall the left hand side, that whole term in the left hand side of this equation number 30? Okay, let us think in a different way. Okay, so this is the solution. Here n1 prime number of moles of solvent are associated with n2 prime number of moles of solute in the surface, whereas n1 0 number of moles of solvent are associated with n2 0 number of moles of solute in the bulk. Okay, so we have two situations. Situation number 1 is the surface phase, and situation number 2 is the bulk phase. In the surface phase, n1 prime moles of solvent are associated with n2 prime moles of solute. That's up to that, it's okay. But in the bulk phase, can you say what is the number of moles of solute which are associated with n1 prime number of moles in the bulk? In the bulk you have n1 0 number of solvent, but you have to find out the value with respect to n1 prime number of solvent in the bulk. So you have to apply the unitary method. First of all, you have n1 0 moles of solvent associated with n2 0 moles of solute in the bulk phase. Therefore 1 mole of solvent are associated with just n2 0 and n1 0 moles of solutes in the bulk phase. Therefore n1 prime moles of solvent are associated with n2, just multiply this with this ratio with n1 prime, so it becomes n2 0 n1 prime by n1 0, and this is the term which is found in the equation number 30, and you have found there the difference n2 prime minus this term. That is, this is the difference in the number of moles of the solute particles between the surface and the bulk, and this is our target. We have to find out the difference between these two, and this is known as the surface excess. If this difference is negative, then surface accumulation is less, and if this that is the negative adsorption takes place, and if this difference is positive, that is positive adsorption takes place, in that case surface tension decreases with increasing concentrations. So this is a very beautiful thing. So we conclude that N1 prime moles of solvent are associated with N2 prime moles of solutes in the surface, and N20 N1 prime over N10 moles of solutes in the bulk phase. So this is the number. N1 prime moles of solvent are associated with this number of moles of solutes in the surface and this number of moles of solution in the bulk phase. This is the final conclusion. What is the difference? This is their difference. So this is the difference with the in the solution where the surface area is S. So what should be the value per unit surface area? So if you divide this whole term by S surface area, then you will get the difference, their difference per unit surface area, and this is known as surface excess. Therefore this term is the difference between the number of moles of solute in the surface and that in the bulk. When this excess surface concentration is divided by surface area S, then this is known as the surface excess, and this is represented as gamma. This is capital letter gamma. Therefore surface excess means gamma. This is actually excess surface concentration of solute per unit area. That is, this is the difference between the number of moles of solute in the surface and number of moles of the solute in the bulk per unit surface area. That is, if you divide this difference by S, then this is gamma. Okay, so what is the value? We have just obtained this value. The difference is this one, and surface area is S, and this is actually the term which is the left hand side of equation number 30. So the in the right hand side of equation number 30, what is there? It is minus d gamma by d mu 2. So we get another equation. Gamma, that is surface excess, is d, this capital letter gamma, and this gamma is small letter gamma. So this gamma is surface excess minus gamma is d gamma. This gamma is surface tension. So d gamma is small gamma over d mu 2, chemical potential. This is equation number 31. This equation number 31 becomes more significant if you convert this mu 2 into concentration, in terms of concentration. So how would you do that? We know that mu has the expression mu 0 plus RT ln A. A is the activity. Now in case of solute molecules, mu becomes mu 2. The pure solute has at standard state chemical potential mu 0. So in case of solute it becomes mu 2 0, and if activity is A, then in case of solute you have to write A2. So the overall equation is mu 2 equals to mu 2 0 plus RT ln A2. A2 is the activity of the solute. If you differentiate both sides, then mu 2 0 is the actually constant term, so it becomes d mu 2 equals to RT d ln A2. Now d ln A2 means dA2 by A2. So we can write d mu 2 equals to RT dA2 by A2. Now if you take the reciprocal of this equation, then you can also write d1 over d mu 2. Here A2 forms the numerator, whereas RT dA2 goes to the denominator. And if you multiply both sides by d small gamma, then it becomes instead of 1 it becomes d small gamma, and in place of A2 you can write A2 into d small gamma. And this term, now you are quite familiar with this term, d gamma over d mu 2, and this is nothing but minus capital gamma, that is minus of surface excess. So this is A2 over RT into d gamma by dA2. That is, if you rearrange this, you will get minus A2 by RT into d gamma by dA2 equals to capital gamma. Now for a dilute solution, in place of activity, you can substitute this by concentration term C2. 2 means that is the concentration of the solute. Then this previous equation becomes, in place of A2 you can replace this by C2, and it becomes equation number 32. What is the equation? Now it is minus C2 over RT into d gamma by dC2, and this is nothing but equal to gamma. So this equation number 32 is known as the Gibbs adsorption equation. So gamma has two expressions. One is this one, just we have obtained this equation number 32, and this is equation number 30. This is the left hand side of equation number 30, which is actually the difference of number of solutes per a particular number of solvent molecules between the surface and the bulk per unit surface area. So gamma has two expressions. Now let's recall this graph again. So here we can explain the term positive adsorption and negative adsorption. So if d gamma by dc2 is negative, that is, this is the curve having negative slope. So this is negative. That means if this curve is negative, d gamma dc2 is negative. This is also negative. So this overall left hand side becomes positive. That is, this capital gamma is positive. So capital gamma is positive. If capital gamma is positive, then this term is also positive. That is, this term is greater than 0. If this term is positive, then this term is greater than this term. That is, the surface concentration is greater than the bulk concentration. Look at this picture. In case of detergent water solution, case 2, surface concentration is greater than that in the bulk concentration. Similarly, in case of salt water solution, d gamma by dc2 is positive. So if d gamma by dc2 is positive, then this overall left hand side becomes negative. So this capital gamma is negative. If this is negative, then this term is also negative. That is, this term is less than 0. If this term is less than 0, this n2 prime is less than this term. That is, the surface concentration is less than that in the bulk concentration that takes place in case of salt water system. So this way these two curves are explained. So that's all about this chapter, liquid state, and this one was the last lecture. And let's discuss one final question of this chapter. Previously we have discussed 11 questions. This is question number 12, and this question is extracted from the IIT-JAM 2021 question. And this question is this one: the surface tension of a solution prepared by mixing 0.02 mole of an organic acid in 1 liter of pure water is represented as gamma prime minus gamma small equals to capital A log within bracket 1 plus capital B small c, where gamma star, this is not gamma prime, I'm sorry, this is gamma star. Gamma star is the surface tension of pure water, and A is some constant, it has some value, B has some constant, C has some C is mole per liter. Okay, and here you can find 0.02 mole per liter is the value C. So excess concentration of the organic acid of surface area, Gibbs equation is at 300 Kelvin is N into 10 to the minus 6. So N is some unknown thing. So we have to find out the value of N up to 2 decimal places. And also given R equals to 8.314 joule per Kelvin per mole. So to do this, in order to do this, we have to start with the equation gamma star small minus gamma small equals to capital A log 1 plus BC. Now C represents the solute concentration, isn't it? So you have to write C2 because this is the solute concentration. So in place of C, just replace this C by C2. It will become more convenient for us in that case. So this equation is actually BC2. Okay, so BC2. Now let's differentiate. Before differentiating, we have to convert this log term into natural log. So if you divide this log by 2.303, it becomes natural log. So small gamma star minus small gamma equals to A natural log 1 plus BC2 over 2.303. So either you divide this by 2.303 or multiply this by 0.4343, whatever you want, according to your convenience. So let's carry forward this equation and differentiate both sides. So differentiating both sides with respect to C2, then this is a constant term, so it will give 0, but this will not become 0. This will give d gamma by dc2, and due to this negative sign, it becomes minus d gamma by dc2, small letter. And with the right hand side, first of all, you have to differentiate this one. So 1 over 1 plus bc2, so A divided by 1 plus bc2. 1 over 2.33 was present already. Okay, so 1 by 2.33 A in the numerator, and this one, after having differentiated, it becomes 1 by 1 plus bc2. Now after that, you have to differentiate this term within the bracket. So differentiation of the term 1 plus bc2 with respect to c2. What is the result? This one gives the result 0 and this one gives the result b only. So 0 plus b. As a result, the numerator becomes ab. So this is the final equation. Minus d small gamma by dc2 equals to ab by 2.303 1 plus b c2. Now from our previous derivations we know that this d gamma by dc2 is obtained in this equation number 32, and this is if d gamma by dc2 minus is multiplied by c2 by rt, then it becomes the excess surface concentration capital gamma. So in place of d small gamma by dc2 we can put this term in this equation. So this excess surface area is nothing but c2 by rt into ab by 2.303 1 plus bc2, because minus d gamma by dc2 equals to this one. So in place of minus d gamma by dc2 we are replacing this by this term ab by 2.303 1 plus bc2. Let us carry forward this equation in the next slide. So in the next slide this equation is appearing. Now what are the values given here? Given that capital gamma surface excess is n into 10 to the minus 6 mole per meter squared, C2 concentration of the solute, that means 1 liter in 1 liter 0.02 mole is dissolved. So it should be roughly 0.02 mole per liter, and since it is mole per liter you have to convert this into SI unit. So 0.02 into 3 mole per meter cube. Okay. A, the constant, has the value 0.03 and this is the SI unit, but B is not given in the SI unit. It's 50 mole inverse liter, that is liter per mole. So it was mole per liter. So to convert this into mole per meter cube we have to multiply it. You multiplied this with 10 to the 3, but this is the reverse. This is liter per mole. So in order to convert this into meter cube per mole, you have to multiply this, instead of 10 to the power 3, you have to multiply this by 10 to the minus 3. So it becomes meter cube per mole. That means mole inverse meter cube. This is the SI unit. And also we are given temperature 300 Kelvin and the universal gas constant R 8.314 Kelvin per joule per Kelvin per mole. So we have to put all these values in this equation, what we have derived. And in place of capital gamma we are putting n into 10 to the minus 6. In place of C2 we are putting this value 8.314 given 300 Kelvin of temperature. In place of A 0.03, in place of B 15 to 10 to the minus 3, and in the denominator 2.303 as usual, 1 plus BC2. So 1 plus this one is B and this one is C2. Okay, and after having solved this equation we get the value of n up to the second decimal place is equal to 2.61. So just input this data and get the full marks. Okay, so go and have success. So thank you and have a nice day.